My name is Allison, and this video is brought to you by the Math and Science Learning Center as part of the Quantitative Methods lecture series. In this video, I will be showing you some basic forecasting methods in Excel and how to find the mean absolute deviation. All right, so let's jump right into our example here. I have a data set of Broadway attendance in millions over the last decade or so. We're going to try and predict the values for 2020. Obviously, with COVID-19, these are not going to be accurate, but I thought it would be interesting to see how our forecasts end up comparing to actual data. So, we are going to try out three forecasting methods. We have a moving average, exponential smoothing, and a linear trend line. So let's start with our moving average. Our moving average is exactly what it sounds like. We're taking the average of our data set values, and those values are changing as we go through or go down the line. So in this case, we're going to find a 3-year average. We could easily find a 2-year moving average, 5-year, 6-year. Doesn't really matter, but the longer period you choose, the smoother your data is going to be. We generally like the moving average for stable data sets anyway. And so, for instance, with our Broadway attendance, it's pretty stable across the board. Obviously not for 2020, but so this would be a nice way of forecasting for this particular data set. So I can't really find it for the first 3 years because I don't have enough data previously to find an average. But once I get to 2015, I have 3 years before it that I can use to forecast this year. So I'm just going to use the average function and take the 3 previous years and hit enter. And because I use that formula, I can just drag it down and find that our projected value in 2020 would be 13.94 million people. Notice that the moving part has happened, right? We're no longer looking at 2012, 13, and 14. We're looking at the 3 previous years to 2020, so 2017, 2018, and 2019. All right, so our next forecast will be exponential smoothing. So exponential smoothing is really nice when we want to give more weight to recent changes in data. Right? The way that we do that is using this little character, alpha. So alpha is known as the smoothing constant. It helps us give weight to recent data. So it's a value between 0 and 1. And when it's really close to 1, that means that we're heavily weighting it towards recent data. This D sub t are these values over here. So that means that when it's close to 1, it's going to be super reactive to what's happening in our data set. So for instance, with this year, as we forecast into, say, 2021, as we're using data from this year, we might want to lower our smoothing constant, right? If we don't want it to be as reactive to more recent years. All right, so I can't find an average or a forecast for 2012 because I don't have data points before it, right? I don't have a data point, I don't have a forecast, so I can't find that one. For 2013, I can find a forecast, but I'm going to have to assume that it's just really close or really similar to the previous year, right? Because I don't have a forecast here, I don't actually have enough to form my formula. So I'm kind of just assuming that both D sub t and F sub t are 12.33, which means that I'm going to forecast for 2013 as 12.33. From there, now I can input my formula. So I'm going to hit enter, right? And I have been told that my alpha is 0.06, and I'm going to multiply that by the previous year's data set. So notice that I'm in 2014, so I'm going to use the 2013 data as D sub t. Plus 1 minus alpha. So if alpha is 0.6, I want to do 0.4 here. 1 minus 0.6 is 0.4 times my previous forecast, which for us was 12.33. So I can hit enter. All right, and I'm going to take that cell that I just put the formula in, and I'm going to drag that down. Wonderful. So I find that in 2020, our projected attendance would be 14.28 million people. Again, Not going to be accurate because of the circumstances, but interesting all the same. Our last forecasting method is going to be our linear trend line. So I'm sure we've all seen lines before in a math class, right? It's the same thing, just with some different variables happening here. So we're going to have to find our intercept and our slope, and then we're going to use our years as our x values. Okay, so lucky for us, Excel has formulas for that. So we just type in intercept, and I'm going to grab my y values, which are my demand or my actual data points. And I'm going to grab my years as my x's to get my intercept, and I'm going to do the same thing with slope. Grab my y's, and then I grab my x's. Great. So I have my M and I have my B. I'm going to take these and use them all throughout this column to find my regression or linear trend line. So I hit enter. I'm going to take my slope. And because I want to keep using that slope throughout that whole column, I'm going to set it with some dollar signs. That means that I'll continue grabbing G15 every time I want the slope. I'm going to multiply that by 2012 and then add our intercept, which again, I want to keep referencing G14, so I'm going to put some dollar signs around it. Then I can hit enter, and because I put those dollar signs, I can just drag this right down the column. Without those dollar signs, you wouldn't be able to copy that formula nearly as easily. Great, and so we find that, if this were an accurate forecast, we would expect 14.74 million people to attend Broadway shows this year. All right, so lastly, when we find a forecast, we do want to make sure that we are at least somewhat accurate. Because there are different forecasting methods, we want to make sure we get the best one. So we have ways of calculating error in Excel to help us see which method might be the most accurate. So absolute error is simply taking the difference between our forecasts and our data points from the original set. Now you can only find error when you have both a forecast and a data point. So do not use this final row because we don't have a data point for that. All right, so if I'm talking about absolute error, I'm taking the absolute value, which is just ABS, and I'm going to do the forecast minus the data point. Right, and I can just drag that all the way down to 2019. And I'm going to do that for all of these. So everywhere that I have a forecast value, I'm going to take that forecasted value and subtract away the appropriate data point, and then just drag that down the column up to 2019. The same thing for my linear trend line. Drag that. Fabulous. So now that I have absolute error, right, I can find my mean absolute deviation. All we're doing is taking the average of those absolute errors. So I'm just going to take the average of each of these. Simple enough. It looks a little bit different on each column because we have a different amount of values. All right. So, as you can see, we have a MAD of 0.87, 0.68, and 0.34 for each of these forecasting methods. Our goal when we calculate error is to go with the smallest one, generally. So as I mentioned, our linear trend line is generally going to be the one that has that because it's designed to have a small error. So the only reason you might not want to do that is because it doesn't react to trends. Yeah, so if there are peaks and valleys to your data, linear trend line might not always be the best option because it's not reactive. But it does have a really low error, so it can be super helpful in that respect. So this has been some of the basics of forecasting. There are plenty of other forecasting methods, and there are a lot of other things you can do in Excel to help you understand a data set. But these are just a few of the things. If you have any questions about what I've covered in this video, or if you have any questions beyond that about forecasting, please feel free to stop by the Math and Science Learning Center, and a tutor should be able to help you there.